All right, today we're jumping straight into a big one. The paper is Sharp Monocular View Synthesis in Less Than a Second.
And this one, SHARP, is a really significant step. It's all about tackling 3D reconstruction from a single photo, and it tries to solve both speed and visual quality at the same time.
Which have always been the two big trade-offs. The core idea here is, well, just how fast it is. This whole thing works with a single feed-forward pass through a neural network.
A huge neural network. And its one job is to regress, to predict all the parameters for a 3D Gaussian Splatting representation instantly.
The numbers they're reporting are, frankly, pretty wild for this space. The whole synthesis, from the 2D photo to the full 3D scene, happens in under a second.
Yeah, 0.912 seconds on an A100 GPU, to be specific. And once you have that 3D model, it renders it in true real time. We're talking up to 100 frames per second.
And that speed is what lets them really push the state of the art for zero-shot generalization. They're reporting, a 25 to 34% reduction in LPIPS?
Right, and 21 to 43% on DISTS. And for anyone listening, those are key perceptual metrics. It means the final images just look better, sharper, and more correct to the human eye.
And critically, this is where it gets really interesting. They're not just a little better. They're outperforming these huge, modern, diffusion-based models.
For nearby views, yes. They're getting better quality than models like Gen 3C while being 2 or even 3 orders of magnitude faster. It's a completely different league of performance.
So the mission, the application here is really clear. It's about enabling real-time, high-res rendering for small camera moves. Think about looking at a photo on your phone and just tilting it slightly to see around an object.
Or, for AR and VR, just handling the natural little shifts in your posture inside a headset. That latency has to be basically zero for it to feel real, and SHARP is designed to deliver exactly that.
Right, and that's been the holy grail for a while. Monocular view synthesis, making 3D from one 2D image, is just incredibly hard.
Oh, it's a classic ill-posed problem. Most of the really high-quality methods in the past, like the early NeRFs, either needed a whole bunch of photos or they had to optimize for minutes, sometimes hours, for every single scene.
So SHARP came in with these two really strict goals: sub-second synthesis and real-time photorealistic rendering, but specifically for those nearby views.
Exactly. And the technology they built on top of is key to that. They use 3D Gaussian splatting as the scene representation.
Which is an explicit representation, right? Not volumetric like NeRF. It's basically a very sophisticated point cloud, which is why it renders so fast.
Precisely. The network predicts about 1.2 million of these Gaussians. They're parameterized over a 768 by 768 grid, and they use a 2-layer depth map to place them in space.
Now, a Gaussian isn't just a dot. It's got a lot of data attached to it. What attributes are they actually regressing for each of those million-plus points?
Each one carries 14 attributes. So that breaks down into 3 for its position in 3D space, 3 for its scale, 4 for its orientation, that's a quaternion, then 3 for its color, and finally 1 for its opacity.
It's a huge amount of data to predict in one go.
It is. I saw in the paper they specifically mentioned they avoid using spherical harmonics for the appearance, which is a common technique.
Is that just to keep the output size of the network manageable?
That's exactly it. SH, or spherical harmonics, they add a lot of complexity and just a ton of extra numbers to the output. Since the whole point of SHARP is this one-shot regression, they had to keep that output vector as lean as possible. So they just rely on the network learning to bake the appearance into the direct color attributes.
Okay, so let's walk through the actual pipeline. They say it's modular, but the whole thing is trained end-to-end.
Right. So you start with your input image that goes into a monodepth backbone. This is a really key component. It gives you some intermediate features and an initial 2-channel depth map.
2-channel.
Yeah, basically 2 layers of depth. That map then goes to a new module they created, the depth adjustment module, which we should definitely dig into. From there, a Gaussian initializer and a Gaussian decoder predict and then refine all those 14 attributes we talked about.
And then the final steps are just putting it all together.
Yep. A Gaussian composer combines the initial guesses with the refined deltas, and the whole set of 1.2 million Gaussians gets fed to a standard differentiable renderer to produce the final image.
And the whole network has, 702 million parameters?
That's the total, with about 340 million of them being trainable. It's a beast, but that's what it takes to learn how to infer this much 3D structure without any kind of slow, iterative optimization.
Let's pivot to the really clever technical bits then. Starting with that depth backbone, getting depth from a single image is, famously difficult. They're using a pre-trained Depth Pro model.
They are, one based on vision transformers. But here's the first really crucial insight they had. In a lot of these systems, you'd take a big pre-trained model like that and you'd freeze it.
Right, to save on training costs and just assume the geometry part of the problem is solved.
Exactly. But the Sharp team found that a frozen depth model actually really hurt the final synthesis quality, especially on tricky surfaces, things like reflections, glass, or even just sharp object edges.
That makes a lot of sense. A model trained just to be good at depth maps might smooth over an edge, which is fine for its original task, but totally breaks the illusion of photorealism for view synthesis.
The geometry and the appearance have to work together. So their solution was to unfreeze parts of the depth model during their own training, specifically the decoder and low-res encoder.
So the error signal from the final rendered image, the view synthesis loss, can actually flow all the way back and fine-tune the depth prediction.
Yes, so the depth map becomes optimized not just for geometric accuracy, but specifically for producing the best-looking novel views. It's a really smart adaptation.
But that doesn't solve the core ambiguity problem, right? Monocular depth is ill-posed. The network could see a flat wall or a slightly curved one, and it might just average the possibilities, which leads to blurry geometry.
And that's where their second big innovation comes in, the Depth Adjustment Module, or DAM. It's inspired by conditional VAEs, but it's much simpler in practice.
Okay, so what does it do?
During training, they have this little UNet that looks at both the network's predicted depth and the ground truth depth. It's an auxiliary network.
And it learns to, what, correct the prediction?
It learns to output a scale map, which they call S. This map basically adjusts the two-layered depth output from the main backbone. It learns the smallest amount of information needed to push the network's prediction towards the correct, stable geometry and resolve those ambiguities.
And the really clever part.
The really brilliant part is that the DAM is only used during training. It's like a set of training wheels. At inference time, when you want that sub-second speed, you just replace the whole module with an identity function. It's gone.
So you get all the benefits of this stabilized geometry during training, but with zero performance cost at runtime. That's fantastic.
It's a perfect example of pushing all the complexity into the training stage to guarantee inference is as fast as humanly possible.
Okay, so once the depth is stabilized, you have the Gaussian initializer and decoder.
Right. The initializer uses that clean depth map and the input image to create a set of base Gaussians, G0, just a sensible first guess. But the real magic, the photorealism, comes from the Gaussian decoder.
That's the part that learns the refinements, the deltas.
Exactly. And it predicts deltas for all 14 attributes simultaneously. The change in position, scale, rotation, color, opacity, it's all learned together. That's what ensures the final geometry and appearance are coherent. Then the composer just adds those deltas to the initial Gaussians, and you're done.
This all sounds like a system that would be incredibly brittle without a very, very good training strategy. How on earth did they teach it to generalize to completely new scenes in under a second?
With a very carefully designed two-stage training curriculum. It had to be done this way to get the robustness they needed.
Okay, stage one.
Stage one is all about learning the fundamentals. They trained it for 100,000 steps on purely synthetic data, a massive data set, 700,000 scenes, 8 million images. In that world, you have perfect ground truth for everything. The images, the camera poses, the depth maps.
So you're teaching the network the basic laws of 3D geometry in a perfect, clean environment.
Exactly. But then you have stage two, which has to bridge the gap from that perfect synthetic world to the messy, unpredictable real world.
And that's the hard part, because for random real-world images, you don't have multi-view ground truth.
Right, which is where their self-supervised fine-tuning, or SSFT, comes in. This is the second stage. They fine-tune for another 60,000 steps on real images from data sets like OpenScene. The trick is how they create the supervision signal.
Go on.
You take a real image, run it through the current model to synthesize a pseudo-novel view, a slightly shifted perspective. Then they swap them.
They swap them. What do you mean?
They feed the newly generated pseudo-novel view back into the network as the input, and then they ask the network to reconstruct the original real image.
Oh, that's clever. So if the model's internal 3D geometry is consistent and robust, it should be able to reverse the process.
Precisely. It's a powerful self-supervision signal that forces the network to learn geometrically consistent representations of real-world scenes. And you don't need any pre-captured multi-view data to do it.
Okay, so that handles the training robustness. Let's talk about the loss function, because the paper's title has sharp in it, and that sharpness has to come from somewhere.
It absolutely does. And the loss is really where they focus on perceptual quality. Of course, they have the standard color and alpha losses, but the real centerpiece is the perceptual loss, L-percep.
Which we know is great for making things look sharp and detailed because it compares high-level features instead of just raw pixel values.
Right. But there's a huge engineering problem. If you apply a perceptual loss across the entire image on a network this big, the memory requirements for backpropagation just explode. The computation graph gets too big to handle.
A classic deep learning bottleneck. How did they solve it?
They call it a computation graph surgery mechanism. It sounds dramatic, but it's a very targeted fix.
Surgery. I like it. So what does it actually do?
It's a memory management trick. During backpropagation, it explicitly precomputes and caches the gradients just at the perceptual loss node. Once it has those gradients, it immediately cuts and releases the part of the computation graph that involves the big ResNet backbone used for feature extraction.
Ah, so it stops that massive graph from accumulating in memory.
Exactly. It lets them train with full FP32 precision without running out of memory on the A100. It's an infrastructure hack that enables the high-quality loss term to even be feasible.
But even with a perceptual loss, sometimes you can get results that are sort of feature level correct, but still a bit blurry or smudgy to the human eye.
And they saw that too. So they reached back into the archives of computer vision and revived the Graham matrix loss.
The Graham matrix, I hadn't heard that mentioned in a while. That's old school style transfer stuff.
It is. But they found it was incredibly effective here. They apply it right alongside the standard perceptual loss on the same latent features from the ResNet.
Why? What does matching the autocorrelation of features get you that a standard L-percep doesn't?
So the standard perceptual loss is about matching the content, the objects, the shapes. The Graham matrix loss is about matching the style or texture. It encourages the network to match the statistical relationships between the features.
So it's looking at the fine-grained patterns.
Exactly. And that specifically combats that feature-level blurriness. It was a huge win for them, boosting their DISTS scores and visual sharpness significantly. The ablations showed it was responsible for up to a 62% improvement in the DISTS metric. It's a critical piece of the puzzle.
So it's this incredibly tuned system then, a fast architecture supported by clever training time fixes like the DAM, and then this really complex memory managed loss function with the Graham matrix to really dial in the final quality.
It really is. And they add other regularizers too to suppress floaters and ensure the geometry is smooth. Every piece is designed to get fast, sharp, and stable results.
Okay, let's turn to evaluation. We know it wins on speed, but how does the visual quality actually stack up?
Well, first, they make a great point about how to evaluate. They focus almost entirely on perceptual metrics like LPIPS and DISTS.
And not the classics like PSNR or SSIM.
Right, because they argue and they show that PSNR is just way too sensitive to tiny geometric shifts. If your model produces a perfect render that's just shifted by 1%, the PSNR score plummets, making it look as bad as comparing it to a flat gray image.
Which is obviously not how a human would perceive it. We don't mind tiny shifts if the image itself is sharp and coherent.
Exactly. So LPIPS and DISTS are a much better measure of perceived quality. And on those metrics, against other zero-shot models like Gen3C or ViewCrafter, Sharp comes out on top across all the standard datasets.
And this is really the core trade-off to highlight for everyone listening. The diffusion models are amazing at hallucinating texture and filling in big missing areas for faraway views. They have this incredible prior knowledge.
But they are unbelievably slow. Gen3C takes over 830 seconds to synthesize one scene.
So more than 10 minutes?
Compared to Sharp's 0.9 seconds. And for its target domain, those nearby interactive views, Sharp is delivering higher quality. So if your application is instant 3D capture, there's just no contest.
The ablation studies in the paper really drive home which of these components were the most important.
They really do. We learned the depth adjustment module was consistently improving sharpness, proving its worth as a training stabilizer. Unfreezing the depth backbone was non-negotiable for getting reflections and boundaries right. And as we just discussed, that Graham matrix loss was absolutely essential for hitting their state-of-the-art DISTS scores.
So finally, let's talk about the limits. Where does Sharp work best and where does it break? What's its ideal operating domain?
It's definitely strongest for those nearby views, where the camera moves less than about half a meter. That covers natural head motion perfectly. It's still better than most other regression methods up to about 3 meters, but after that, the quality does start to degrade.
Which is a common failure mode for all regression-based methods, right? You're asking the network to extrapolate way too far from the single input view.
Exactly. And the other failure cases are all tied back to that initial depth of prediction. The whole system is only as good as its first guess about the scene geometry.
So what kinds of images trick the depth model?
Macro photography is a big one. The strong depth of field effect makes it really hard to figure out what's background and what's foreground. Also, complex, non-planar textures, like a photo of a starry sky, can sometimes be misinterpreted by the depth model as a weirdly curved surface.
And I'm guessing reflections are still the ultimate challenge.
Oh yes, complex reflections in water, for instance.
Right.
The model often sees those as real, solid objects that are far away, leading to completely nonsensical 3D geometry.
So wrapping up, the big takeaway here is that Sharp has really proven that high-fidelity, genuinely real-time view synthesis from a single image is possible. And they did it with a pure regression-based framework, focusing on smart engineering and a very carefully constructed loss function.
And looking forward, the authors themselves suggest the future might be in hybrid systems. You could imagine combining Sharp's incredible speed and nearby quality with the diffusion model's ability to handle faraway views or complex in-painting. That could be a system that gives you the best of both worlds.
Which brings us to a final thought for you, the listener, to chew on. Sharp has demonstrated that you can get robust, generalized 3D geometry inference from a fast, feedforward network instantly. So if you consider this shift away from slow, iterative optimization, the whole NeRF era, and toward instantaneous regression, how could that change the way we design 3D capture systems outside of just view synthesis? Could a model like this become the core geometry engine inside every smartphone, enabling instant 3D capture for everyone?